A warm greetings to everyone. I am Selvi, Assistant Professor, CSE Department, RMD Engineering College. Subject code 22CS 201, Data Structures, Theory course with laboratory component. Unit 4, Graph, Data Structure. Graph data structure will come under nonlinear data structure. Linked list will be a linear data structure. So the difference between linear and non-linear data structure is, in linear data structure, the memory will be static, that is a fixed memory allocation will be done. But in non-linear data structures, here what are the sequence that it will be as per the names, it will be non-linear, that is discontinuous of memory location and will be connecting it. A binary tree is a graph with some restrictions. Now we are going to see how we are representing a binary tree with a graph. So a tree is an unweighted, directed, acyclic graph. Every node in degree is at most 1 and out degree is outmost 2. The meaning is, in a binary tree, each node can contain a maximum of only 2 nodes. So that's why the in degree value is at most 1. That is, it can hold a 0 node, that is no node, or a 1 node, that is the parent node or a leaf node. Out degree, so that is each node can give a branch to 2 nodes. So that way it makes the maximum of 2 nodes. So that will be exactly one path from the root to the every node. You can also represent a linked list in a graph manner. So we can say a linked list as an unweighted DAG means directed acyclic graph in and out degree of almost 1 for all the nodes. That is, each node can have a maximum of only 1 node to the connection. Here the node A will be connected to the maximum, it can have 1 node connection, or there will be no connection. That is only that will be the only 1 node in the list. So, okay. So the in and out degree for a linked list will be have a maximum of 1. But for a binary tree, the in degree will have a maximum of 1 and out degree will have a maximum of 2. Searching for a path from one vertex to another. So we will be searching a graph. In graph, all the nodes are interconnected. So to travel from one node to another, we can have a many paths are available. So paths will be considered as a sequence of edges, or you can say as a sequence of vertices from one vertex, that is from the source to the destination. Now we can find the shortest path. So as per the graph definition, there will be a more path. So to find the shortest path or the minimize path length or the minimize path cost is mandatory. If we consider the path from SFO to DFW, if you consider here from SFO lakhs $60 plus 120. So using, if you're going from SFO LAX DFW, so total length will be $180. If you go through this path, 70 plus 80, that is SFO ORD I mean 80, totally 150. So comparatively, $150 will be the shortest path. So to finding the shortest path is a very big task in a graph data structure. graph traversal, we have two types of traversal, depth first traversal and breadth first traversal. In depth first search, finding the path between the vertices by exploring each possible path as far as possible before backtracking. That is, will be from, I will explain with this example, then only this definition will be easy for you to understand. You can starting the traversal from any node randomly. I'm starting from A. From A, the path is B. First, I will write the edges from each node. For B, the edges will be from A to B. And for C, the edges will be A, B, E, F, C. And for D, the edges will be A and D. For E, A, B, E. For F, A, B, E, F. For G, A, D, G. And for H, A, D, G, H. The pseudocode will contain the parameters V1 and V2. So it will recursively call the function and we will find the path. If we will be visiting each node in the graph and will be traveling in depth until we find the adjacent node at the last. And if we didn't find any other nodes, we'll be backtracking to the edges of the previous node and find a path. When we are visiting each node, we will make the node from unvisited to visited and will be trace the path. So from the DFS pseudocode, we guarantee that we find a path if one exists. It is easy to retrieve exactly what the path. DFS is guaranteed to find a path and not necessarily the best or the shortest path. It will find a path. So the DFS from A to F will turn the path as from A, it will go to E, and from A, it will go to D, and from D, CNF. Breadth first search. So the difference between depth first search and breadth first search is, in depth first search, while traveling, each node will be traveling in depth in one direction until we find a node. When we are in deadlock, will be backtracking to the previous node to find any other edges. But in depth first search, we will be searching, we'll be traveling the path in breadthwise before we're forwarding to the adjacent node of the another node. So finding a path between two nodes by taking one step down all paths and then immediately backtracking. BFS always returns the shortest path, but DFS is not mandatory to find the shortest path. It will define a path. That's it. The first step will be write the adjacent edges for each node. For node B, the adjacent edges will be A, B, and C, it is A, E, F, C, and D, it is A and D, and for E, it is A and E, and F, A, E, F, G, A, D, G, and H, A, D, H. So the parameters for a BFS algorithm, BFS function will be the source and the destination. So V1, V2 will be the source and destination. We'll be using the Q data structure because first it follows the principle of first in, first out. In DFS, we'll be following stack data structure. It follows the principle of last in, first out. So why we are using that different data structure is in DFS, we will go in depth. That's why we will using stack. So the topmost will have the recent node and we can able to backtrack the edges. But BFS will be traveling the only one step down, and if you don't find a path, will be backtracking to immediately to the previous edge. Previous node. So that's why to it means we'll be pulling out the first element in the queue. So first in, first out. After finding each element, after passing through each node, we will change the node from unvisited to visited. In BFS, it will find the shortest path. If it is an unweighted graph, it will find a minimum cost path. If it is a weighted graph, it won't be always the minimum. So in BFS, it is exploring many possible paths in parallel. So it is not easy to store a path in progress. So the solution for this is we can backtrack by storing preceders for each vertex. DFS uses less memory when we compare with BFS and is easy to reconstruct the path once found, but BFS does not always find the shortest path. The expected runtime for DFS and BFS is order of number of vertex plus number of edges. Thank you.